All right, so we did a little bit about transactions and capacity last time, but just to get into the topic a little bit. So we can first start by considering a couple of basic models of how transaction processing systems work. So first one, we say banking. Okay? Banking's interesting because the customers are fundamentally isolated from each other. Typically, you don't have simultaneous access to the same data, right? Everybody accesses their own account. Now, it is possible for multiple users to be connected to the same data. For example, if my wife and I share a bank account, we could be at separate ATMs trying to withdraw money at the same moment. So it is possible that you could have two people looking at the same time, but it's unusual. The other thing is, if you know about required reserves, banks are required to have a certain amount of assets available on hand. They can't just lend out everything they have. And so every customer transaction, they do affect the bank reserves. So there's a little bit of concern about simultaneous access to the same data, but it's pretty minimal. On the other hand, in the case of banking, if people do access the same data simultaneously, it could be a big problem, which we'll talk about shortly. Retail, on the other hand, simultaneous access to the same data is entirely routine, right? If you imagine a physical store, you have people randoming around, walking up and down the aisles, looking at the same stuff all the time. It's the same thing in an online environment. In a retail site, you can have many people looking at the same product page at the same time, many people attempting to grab one of items from the same pool of inventory. So accessing the same data is pretty routine in a retail environment, but most of the time, it's not terribly dangerous. Now, there is another case, middle ground, reservation systems. So if we think about that, people trying to buy tickets for the same flight or for the same concert or for the same hotel room, stuff like that, then yeah, you really have to be careful and make sure that you don't oversell the same tickets. Anyway, so we can talk about how their transaction processes differ, but that's just a little, bit to get us started about some of the typical problems you see as far as simultaneous access to data. Now, all this is known as concurrency. So concurrency, basic problem here, what happens if two people try to access data at the same time? That's what concurrency is. Concurrent access means two or more people accessing the same data at the same time. And of course, this can be a problem in a variety of ways. The simplest one is simply two people trying to withdraw money from the same bank account at the same time. Now, why this is a problem, let me take a moment to consider this. Why this is a problem is because the banking system doesn't, not everything is guaranteed to be isolated from everything else. So here's ATM, and here's the other ATM. What could happen, what should happen if you have two simultaneous withdrawals, it should be something like, let's say the balance is, well, let's make the balance $500, okay? Suppose I withdraw $300, okay? What should happen, new balance, $200, and then this other transaction goes through. He sees balance 200, withdraw 300, fail, right? That's the way this should draw. It should go here to here to here, right? That's the way the banking system wants it to work. However, the problem is that's not really how the banking system works. What happens is both people look at it at the same time, and they see, oh, balance 500, great. And suppose they launch two simultaneous withdrawal requests. Okay, so I'm gonna mark that over to the side here. Simultaneous withdrawal requests. Okay, so at the same time, withdraw 300, and over here, withdraw 300. Now, what will happen is in some application that's not actually on the database machine, some application will look at the current balance has that in its memory, says, oh, there's $500 here. I can pull 300 from that. Likewise, the same thing will happen over here. And each of these will send a write instruction to the banking account to say, here, I've calculated the math, write the new balance. Whoop. And in the end, right, the new balance shows as 200. This is a big problem, right? Because number one, if you could do this and get away with it once, well, that is a very serious problem. But if you can do it once, you can probably do it more than once. And if you do it more than once or have multiple people involved that you can simultaneously have them try to withdraw money, then suddenly it doesn't matter what the balance in the bank account is. You can just withdraw a whole bunch of money and get away with it. So in practice, what you need is some kind of governing structure, right? You basically, to prevent the problems associated with concurrency, concurrent access, you need some governing application to check whether transactions are already in progress, right? Because if you do that, if you say, hey, when whoever tries to do it second, the number two person tries to withdraw the money, they'll say, oh, sorry, that data is currently involved in a transaction. Please try again in a few moments. And then once that goes through, then the second person can try to do it and they'll get the correct information. If you don't have that kind of governing structure in place, then you can potentially see this problem, which is very serious. Okay. So back to our slides. Now, how do you deal with this? Well, one possibility is you simply don't allow simultaneous access to data. You say, if somebody is already looking at the data, nobody else can. Secondary users are locked out. Another possibility is simply to prevent writes. So you could say, yeah, anybody can read the data, anybody can look at it, but you can only change it if you're the only viewer looking at it. So it says, yeah, you can look, but only one person at it. Anybody can go into the ATM and check the balance, but only one person at a time could withdraw money. The other possibility, changes are permitted if there are more than one viewer, but it has to be immediately updated for all viewers. So this is obviously in sequence of reduced strictness. So no simultaneous access to data. You prevent all the problems associated with concurrency. You say, well, there can't be any concurrent access, but it also limits what your system can do. For example, suppose you go to Amazon, one of the things you'll see, if you look at a product page, you'll see how many of that thing they still have in stock. Well, if you say nobody can simultaneously access that data, nobody can actually see that information at the same time, right? Because you quite often are going to have many people looking at a product page and looking at that count of how many things are still in stock. So simple stuff like that would be prevented. Also, imagine if two people have a bank account, one person has a bank account, but it gets hacked and some other person on the other side of the world has access to it. Well, just by the fact that that person is looking at the bank account would prevent the actual owner from going in and looking at it at all. That would be potentially a big problem. Similarly, like if you have a Facebook account that gets hacked, which is a pretty common thing, then same problem, right? Once your account gets hacked, you literally cannot get in to do anything with it. So these are problems that you maybe don't want to have happen when you consider that the costs of the problem are fairly small. For example, a hacked Facebook account, it's an annoyance, but in most people, for most of the time, it's not going to do any real damage. So anyway, so to consider which of the policies is appropriate for a particular organization, well, number one, how many users there are and how often simultaneous access happens. That's significant, right? The more users you have, and if they tend to be clumpy and look at the same things, then simultaneous access becomes more of a concern. Number two, system complexity. If your system is quite complex and you think you know exactly how it runs, but there's some weird stuff in there and maybe you actually kind of don't, then you probably want to be more cautious. There's a good case of this with one of the Bitcoin exchanges. Had about 5 years ago had a hack for about 20 million worth of Bitcoin because fundamentally the system was more complex than they were prepared to deal with. Yes, Coinbase, Poloniex. There have been many Bitcoin hacks, right? But this was the one. If we want to take a minute, we have time to do a little excursion here. Oh, they had another one. This one. Oh, hey, they got them. Maybe. All right, so this one, again, was from a few years ago. So the short version, right, this is here. Hacker discovered if you place several withdrawals all in practically the same instant, they get processed at about the same time. Temporary negative balance, but valid insertions into the database, which is that red stuff that I had drawn down here. This is exactly what happened, except, you know, many more of it. And then eventually it gets checked, right? They get picked up by the withdrawal demon. So yeah, for a little while, you have a negative balance, but all the transactions have already gone through and they've already sent you the Bitcoin numbers, and it's just too late to recover from it. So that is a serious problem. And again, fundamentally, the guys that were doing that, you know, they were math guys, they were computer science guys, but they weren't really network database guys, where they would have known, hey, that's a serious problem. We can't really allow that to happen. Their governing mechanism was there, but it was too slow. It didn't catch up with stuff in time. All right. And of course, the last one, in many cases, this is the most important. Importance of data integrity versus response time. I suppose it's the most important because it encompasses a lot of these factors. In some cases, data integrity is hugely important. For example, if you do a transaction, if you actually buy something and there's money involved, data integrity is very, very important. And the more money is involved, the more important data integrity is. On the other hand, there's a lot of data out there where integrity is not that important. For example, if you go to Facebook and there's a picture there, somebody posted a picture of their dog, and you click the like button on it, it doesn't really matter what sequence those likes are received in, right? If there are 50 people that are liking on it within an hour, it doesn't matter if they get processed perfectly in order. It doesn't matter if it's down to the microsecond that it happens. It doesn't matter if there are 2 different copies of the image at different data centers that have slightly different batches of likes for a few seconds. None of that stuff really matters. It'll get sorted out. Facebook has a policy of what's called eventual consistency, that, you know, they resolve that stuff when they get around to it. Again, typically within a few seconds. But response time is very important. So what's important at Facebook is that if you click on an image, that you immediately see your like has been registered, but you can't look at the whole rest of the world anyway. So it doesn't really matter if it takes a few seconds for it to get to the other data centers. So Bitcoin, data integrity, very, very important. Facebook likes, not so important, right? Response time becomes more important. So if you're doing a large scale cash transfer, right, then you're willing to accept a certain amount of delayed response. For example, we refinanced our house early this year. In fact, we're doing it again right now because interest rates are crazy low. We refinanced it, and I had to get the balance of the house under a certain threshold. So I pulled some money out of some things I have. And to do a wire transfer like that, there's actually basically a 24-hour delay. They say, yeah, you put in for it now, it'll go through the next day. And I suppose that's to prevent any sort of problems with, you know, people hacking the system and me not knowing and the money being gone afterwards. So it gives me time to recognize that a wire transfer is going through. But yeah, if you're doing a big transfer like that, you don't expect it to, you know, be super easy. You expect there to be a certain amount of checks involved. All right, so that's the stuff about concurrency. Now, other things related to this, atomicity and isolation. Okay, so atomicity for a transaction means that if there are a group of related tasks, either they're all completed or none of them are completed. So for example, if I go to buy some stuff on Amazon and I try to pay with my credit card and I type in the number wrong, the credit card will be declined. And that means a whole bunch of cascading secondary transactions are also not going to happen. The goods won't get sold, the inventory won't get reduced, the relevant analytics in Amazon don't get processed, no payment is received, okay? None of that stuff happens. So at the end of the day, the whole transaction, everything involved in the transaction is all pointing in the same way that says this transaction didn't happen. and that prevents consistency troubles down the line. Now, ensuring this sort of atomicity, it can be within an organization, it can also be across organizations. For example, if Amazon is involved with shippers, it's involved with credit card companies, it's involved with the seller of the item, all those different databases across organizations, they all have to be processed correctly. And again, either show the transaction went through or that it didn't get through, but they all got to be pointing the same way. Now, related to that, isolation. So isolation is this, basically. This that we talked about the ATMs. What we want is to have all transactions happen in a self-contained bubble. Okay, so these are isolated transactions, which is to say this transaction is not affected by the second or any other ongoing transaction, right? Basically, it's going to work the same way as if it were the only transaction in the system, regardless of what else is going on. That's what isolation means. This case down here, not isolated transactions, right? Because the fact that there are multiple withdrawals going on simultaneously is going to affect how the system processes them. Okay, here, this whole thing happens first, then this second thing happens first. In this case, both transactions get to see some intermediate results of an ongoing transaction. They're interleaved like that. And that is fundamentally where the problem comes from. Okay, so isolation is all those restrictions placed on access to data. There are big concerns. Number one, when updates become visible to other users. In an isolated transaction, you only see the initial state or the final state of the transaction. You don't see any of the intermediate states where the transaction is half finished, or you don't have, like again in our paint case, where both sides could see, oh, look at that, we're accessing it in the middle, right? It would have to be like the green box on top. The whole transaction goes through before anybody else can access that same data. Okay. Anyway, in practice, isolation is a trade-off with currency. You can't get both. We'll talk about that now. Well, I guess I should talk about it now because I don't have a space for that. Okay, so isolation is a trade-off with concurrency, and the reason why is that anytime you have concurrency, you're allowing multiple users to access the same data. By definition, you're breaking isolation to a point. So there's not really a way that you can say, we are going to have isolation and we are going to have concurrency. It's a question of how much of one or the other are you going to have. And again, importance of data integrity versus typically response time. The more hoops you make people jump through to wait for other ongoing transactions, the slower response time is going to be. For example, imagine if you have a very large database table, right? This is where some problems can happen. Imagine that you have a very large database table with, let's say, hundreds of millions of rows. Okay, so maybe it's well, it could be a long table of invoice data for for a large organization, for a large business. Great. So you have this monstrously large table. Anyway, because the table is large and may be involved with other large tables, queries on the table take a long time, right? This is one of the things that organizations used to see before everything shifted to the cloud. They would say, wow, these tables are so big, they're spreading across multiple pieces of hardware, and instead of having everything be in RAM and get processed pretty quick, things are getting processed at network speeds because every query involves a whole bunch of back and forth in the network, and that takes a lot more time. But if you enforce strict isolation on this kind of system, what happens? Well, if a query is running then the database, for all practical purposes, is locked up, right? If you say nobody can simultaneously access the data, well, guess what? I'm running this big query. It involves a couple of very important tables. While that query is running, I'm looking at that data. Nobody else can access those tables. It is a big problem, right? And then again, if the system is busy, once one operation gets delayed, there will be a backlog of similar tasks. And at some point, you know, and things may, and operations can time out. And eventually, you realize you need to back off on the isolation requirements or redesign the system. Redesign the system in some way to allow faster queries. All right, so this is the sort of thing that happens, right? If you insist on complete isolation, you say, we think data integrity is super important and we're gonna make sure it's always there. Well, guess what? That's gonna slow your system down and that's gonna potentially have very serious negative consequences. All right. So, next thing, rollbacks. Rollbacks are the ability to recover from uncompleted transactions. So for example, you have some transaction in progress, you entered in an invalid credit card parameter, right? So the card is maxed out, you press click, the numbers you enter in are valid, but it goes to the credit card company and they say, nope, sorry, no more credit, and comes back, sorry. Or if there's a failure during transaction, right? So some server shits itself while the transaction is ongoing and you lose what's going on. Or the user unexpectedly disconnects from the system. All sorts of things like that are fairly routine and you need to have your system be able to recover from them. The basic method for rollbacks is you keep a file of all transactions that have been started but haven't been finished, and you track the initial state of any data associated with them. Now, if that data is isolated, that means, in a sense, somebody's already looking at that, so nobody else can get in there and change it while it's going on. You have to have some sort of mechanism for a failed transaction to eventually time out and that data to become accessible by other users. But anyway, when a failure happens, if you have all this data, if you have, you know, the initial state of the data, you simply roll it back. You push back the state of those data items to however they were before the transaction was started. And again, if they're all isolated, then the sequence doesn't matter, but sometimes it could, and you would basically do them in backwards order. So whatever was going on, you know, you roll it back one at a time. Anyway, maintaining rollback record is extremely important because if you have a large scale failure, for example, a big fire in one of your systems, then yeah, the ability to roll all that back and restore it to its initial state is very, very important. Not having that would be very expensive. So rollbacks are important. What are they for? They're for transactions that fail. So you can return the system to its pre-transaction state. And all this brings us, these concepts that we've talked about, isolation, concurrency, rollbacks, all bring us to a system called two-phase commit, or a process. So the point of two-phase commit is if you have a bunch of linked databases, you want to make sure they have the same values after a transaction happens. So again, they're all pointing in the same way. Either all of those related databases say this transaction happened, or they all say it didn't happen. They're all pointing in the same direction. So, for example, customer makes a bank withdrawal using an ATM. The system needs to ensure that the numbers that are on the ATM's interface matches whatever's in the back office database, that the account balances line up, for example. It shows that money went out on both. And then the follow-up, any secondary transactions throughout the enterprise. So for example, if there are multiple replicas of that data stored at other locations, that has to be updated. If there are analytics that the bank does, that gets updated. Any effects on the bank's reserves, that gets updated. So basically the two correct outcomes. Number one, if the customer gets the money, then the back office database should be updated correctly to show that. Or if the customer doesn't get the money, the back office database should be unchanged to reflect that the customer didn't get the money. Okay, so that's two-phase commit. Now we're going to walk through the process. So I'm going to lift this. It's a very nice image, but it still works better in Paint. Okay. Now, what happens here in two-phase commit? Well, suppose this is our transaction coordinator. All right, so transaction coordinator, TC, is a governing process that tells the set of systems what to do. Okay, so we talked about having governors in our system that basically say, this data is busy, you can't do anything with that. It's that kind of system. Resource managers over here, these are RMs, and basically software agents, right, little applications that manage one or more databases. Okay, those are the resource managers. Now, over here is me. Suppose I initiate a transaction by clicking buy it now. All right, so first thing that happens, the transaction coordinator, TC, tells RMs to pencil in changes to the databases. Okay, that's the first thing. So it says, resource managers, there's a transaction about to happen, pencil in some changes to your database. We're not sure if this transaction is going to go through. It probably will. Most transactions do. But for the moment, get prepared to do this. Okay. So the resource managers, they do a few things. And when I say pencil in changes, right, I'm speaking metaphorically. It's the resource managers know that something's going to happen, but they aren't making any permanent changes yet. So resource managers tell their databases to, number one, pencil in changes, and number two, prepare rollback records. Okay, that way, if something goes wrong with the transaction, they can restore it to its initial, the system to its initial state, but they know what they need to do to put the changes in the database because they've, penciled in the changes. Okay, then one at a time, when the databases have informed the resource managers that they are prepared, the resource manager can tell the transaction coordinator. Great. Okay, so one at a time, all these databases, they tell their resource manager, yep, I'm done. When every database belonging to a particular resource manager has confirmed that they're ready to go, the resource manager can respond back to the transaction coordinator and say, okay, we're ready to go too. So at this point, if the TC hears back positively, I'm going to put in plus from all databases. Let me just do that. When it hears back positively from all databases, it knows the transaction can begin because everyone is ready to go. Okay. Otherwise, the transaction will be canceled due to, timeout. Basically, the transaction coordinator has been waiting for a long time. It doesn't hear back, or, or a negative confirmation. People say, nope, we couldn't do this for whatever reason. So, but typically, yeah, it's going to happen due to a timeout. So the resource managers are going to try to do the stuff they're supposed to do. If they can't do it, if for some reason, one of the resource managers fails, for example, then the transaction coordinator simply wouldn't hear from it in time and the attempt would fail. All right, but if it goes through, transaction coordinator tells all RMs to make the changes to the databases permanent, right? We're no longer penciling the changes. Now we're actually doing them for real. So again, resource managers tell their databases Number one, make changes permanent. Sorry, I can't see behind this window of faces. Make the changes permanent. And that's pretty much it, right? If they can. So, as before, when all DBs have made the changes permanent, the RM can respond positively to the transaction coordinator. Okay, so once all this is done, once every database for a resource manager says, yep, we've done it, we've made the changes permanent, then the resource manager can tell back to the transaction coordinator, yep, we're all done. So again, if TC hears back positively from all resource managers, it knows all is well. Basically, all these related systems, they've all completed the transaction, everything's good. Otherwise, a failure, and they're gonna roll it back. Okay, so if the transaction coordinator waits the appropriate amount of time, it doesn't get a positive confirmation from the various resource managers, it's gonna send out a notification, hey, you guys gotta roll all this back, this transaction is not happening, we're done. And I should add here as an epilogue, if the transaction is successful, eventually the rollback records will be discarded, right? Or you don't really need to keep them for a long time for transactions that have actually gone through. Okay. Questions on this? Does this make sense? This is kind of the centerpiece of the transaction process. So remember, a key point about two-phase commit is simply that you have a bunch of databases managed by different resource managers. The transaction coordinator wants to ensure that at the end of the day, you don't have different databases showing different results. You don't have some of them showing that the transaction went through and others showing that it didn't. And two-phase commit is a mechanism for ensuring that's true. Okay, now if you're interested, and I'm not saying you should be, but if you are, I'm just going to show you here the amount of hassle I'm saving you with that distilled version. This is a quick reader on Oracle's procedural gateway, blah, 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 about implementing two-phase commit. All right, there's a whole bunch of stuff here about how to actually set it up in a system, just to give you an idea of that. But what I gave you, that's how two-phase commit works, and these are just specific implementation details. All right. So this is a simple write-up of the same thing, so we can skip that just to get stuff done that we need to get done. And here, another little article on Oracle, same kind of thing about two-phase commit, but briefer. Okay, and that's it for transactions. The other part is capacity. So let's talk about capacity for a little bit. Let's see how many slides we got. Okay, about 11. Good. So network capacity basically means how much data the network can push through per unit of time. And even though there's an absolute limit to how much data the network can push through, what we're really interested in is performance level, right? Basically quality of service. So if the network is meeting all of its assigned goals and getting the data where it needs to be fast enough, it has enough capacity to do what it needs to do. But the problem is, right, there's a lot of different metrics for how capacity is measured. We could talk just in terms of the amount of data getting pushed through. We could talk about the number of simultaneous connections, different combinations of applications, and any mix and match of those various factors. But for now, let's just think of it in our heads. When we talk about capacity, we need the ability to send through a certain amount of data in a certain time. Okay. Now, again, network can only process so much traffic. There is a hard upper bound on how much you can send through. But capacity isn't monolithic. It's not just one single number. We can't say this is how much capacity we have because there are different kinds of traffic categories. So number one, different applications. And even within different applications, the way that data is broken up. In general, it's a lot harder to send a lot of small packets from a lot of different users than it is to send large slugs of data from different users. So think about it. sending a large slug of data is basically like pouring water down a pipe, and it goes pretty smoothly. But if you're sending a lot of packets in, it gets basically, I don't know, frothy, if you want to look at that. So imagine like a bunch of guys tossing in drops of water into pipes. It's going to be more chaotic. It's not going to flow through as neatly. That's the same basic idea with network traffic. If you send a large amount of data through at one time, the user is going to listen for the network being clear. It's going to be clear. As soon as one packet finishes sending, the data link layer is going to push the next packet through, or the link layer is going to, and it'll all happen with a minimum of gaps between the packets. But if there's a lot of different users sporadically sending packets, then the whole transmission scheduling scheme becomes a lot more chaotic, and there's going to be back off delays. There's going to be some more chaos. So it's harder to push through data like that. Anyway, so for a variety of reasons, capacity, even though you say, well, we have capacity X at this time, it might not play out so well at other times. Now, capacity versus quality of service. So capacity is just the amount of traffic the network can handle. And in the short term, it's going to be fixed. So whatever network infrastructure you have, whatever grade of cable you're using, whatever switches you're using, that's going to determine how much capacity you have. And you can, of course, improve that given enough time by adding or upgrading components or splitting the network in various ways. Quality of service just means how well the network is serving its users. So are the users happy? Is the data getting through fast enough? And the big determining factors there, number one, available bandwidth, right? So how much capacity the network has, and other factors like latency, jitter, and loss. So latency is the delay from packets getting to point A to from point A to point B. We know, we sometimes just call it lag, but latency, people don't like it, but sometimes it's manageable. For example, for an email application, latency is not going to bother us that much. For a real-time first-person shooter video game or for voice over internet, yeah, lag is going to bother people a lot. Jitter when packets, some of them are delayed a lot, some of them are delayed a little. Again, that can cause similar problems to latency, but it's less predictable. And typically you solve that through buffering. And of course, packet loss. In some cases, packet loss is not that big of a deal. Again, any true real-time application, chances are loss is going to be manageable when it happens. But if it's something around a transaction where data integrity is crucial, then packet loss is obviously going to invalidate that. Anyway, so the relationship between capacity and performance varies by application and the use of buffering. So for example, streaming video, then latency and jitter are typically going to be worse than small packet losses. If it's a true streaming video, if it's live streaming, then a packet loss here and there, you might lose an image frame or a partial image frame, but the stream is going to keep on rolling and you'll barely notice it. But other applications requiring accurate data, latency and jitter aren't so much a problem as long as the data eventually gets there. And then networks need prioritization schemes to provide adequate quality of service for all applications. So for example, if you have a real-time application, you want to typically minimize latency and jitter because that's what people are really going to notice. On the other hand, something like email, you often push that to the back of the queue because it doesn't really matter if it takes an email like 30 seconds or a minute to get there, but if you're talking voice over internet and it takes you 30 seconds to hear the word from the other person, you're really going to notice that. Anyway, quality of service typically can be improved by, number one, by reducing congestion, sure, by putting less traffic on the network. One way to do that is to smooth out demand. So to a point, many networks can say, we have some operations going on during the day that we could push off to off hours. So things like various checks on the database, make sure that different copies of the database are all mutually correct. That's the sort of stuff that can often happen in the off hours of the business when things are slow. And businesses back in the day, again, pre-cloud, businesses would often find that shifting operations like that would really help out their network capacity a lot. So that's one kind of smoothing demand. Another thing, increasing capacity, right? So just putting in higher grade of cable throughout your network, that'll probably help too. Or adopting a higher throughput wireless standard. So going from 802.11n to 802.11ac. But you need to get new hardware for that, and it's going to be expensive. Okay. Now, when you don't have enough capacity, what happens generally is just like a traffic jam, but with a network. So there's going to be some kind of delayed transmissions at some point. So there's going to be backlogs at individual nodes. So if you recall the example I had with switches back with network infrastructure, same kind of problem, right? That's basically what it is. If there are too many people trying to push too much data through the network, not everybody is going to get all of their data quickly. In some cases, you can even have packets be dropped because transmission queues get too full. So for example, a switch might have some associated memory that it stores incoming packets in. If the switch is backlogged for a bit and can't push out in one direction all the traffic it wants to send, excuse me, it'll store packets there in memory. But if there's a continuous backlog and new packets keep accumulating at that switch, eventually the switch's memory is going to be full, and it's going to drop some of those packets because at some point the memory is full and the next packet in will either push out an old one or will have to be discarded itself. Now, if you're using TCP, those lost packets are in a sense recoverable because the system is designed to say, oh, you didn't get this packet. I didn't receive the handshake back from when you should have received it. I'm going to send it again. Problem is, if your system is already busy and you're getting packet drops because the transmission queue is full, then TCP is just going to inject additional traffic into the network and probably make things worse. UDP, on the other hand, if the packets get lost in transmission, they're simply gone. UDP doesn't inherently have a mechanism for recovering from that. So, other things, applications can fail by timing out. If there's an application that needs to be repeatedly confirm that you're still connected, then if you don't get that kind of handshake back and forth, you might get disconnected after a few seconds. Anyway, so for individual applications, insufficient capacity, you can see various failures, like the application expects to get some data within a certain amount of time, it doesn't get it, so it quits. For example, a transaction process. Maybe there's a 5-second tolerance for how long it takes to get a credit card transaction confirmed, so you send it out, but their system is too busy, and it times out, and it says, oh, sorry, we can't get to it, we'll try again a little later. And generally, that's going to be associated with increased latency. So the busier the system is, right, if you don't have enough capacity, then of course, everything you're trying to do is probably going to take longer. In particular, streaming video, it might seem choppy because you're not getting every frame, or it might be otherwise poor quality. It might go down to a lower grade of video quality. So insufficient capacity, depending on the application, you can have different negative effects, but none of it's really good. Okay. Now I have an old case here from Cisco. Some of this stuff is relevant, some of it not so much. But one thing that's interesting to talk about. So Cisco from the late 90s, early 2000s was seeing a big spike in network traffic. And a lot of it was from new applications like voice over internet and streaming video that are extremely data intensive. And again, this is 20 years ago, so the capacity wasn't quite what it is now. What they did, one case I want to look at. So first, I'll mention two things, two highlights from the case. Number one, Cisco found that just one dude in their organization was responsible for like a couple % of network traffic because he apparently had high access credentials, high priority within the system, and he was doing a lot of file transfer and video streaming, probably porn, I don't know. But it was just a big capacity drain on the whole network. So like one guy in a big organization was a noticeable chunk of data. So what they did is they basically said, oh, we're gonna dial that down. We're gonna throttle your access. You know, no one user should have that amount of data. We can do that by reducing your priority. The other thing that's interesting that is currently, even though this is an old case, still topical, uneven distribution across applications and users. So what they wanted to do was plan going forward, figuring out what their network capacity needs were going to be. And even if you say, well, we're going to the cloud, we don't need to worry about what our capacity is going to be, well, guess what? You still need to worry about what your cost is going to be. So if you're going to do projections going forward about how much system resources you're using in the cloud, that's going to translate into how much you're going to pay. So it is still important to understand. Now, the particulars of this, all right. Cisco has a bunch of different work groups using different applications and with different data requirements. Okay, that's the key point. Now, how do they plan for capacity requirements going forward? Right? So here's the thing. If they just assume all departments are growing by 50%, well, that's probably not, you know, probably about right on average, but can miss some very important details specific to individual work groups, right? Some might go up by 200% and others basically flat, maybe 10% growth. Okay, so that's what they need to figure out. And the other question, how much data do those work groups require now? Is it 200% from very low usage, so not a big deal, or 10% from very high usage and potentially quite significant? Okay, so these are the things. Now, the way that the solution, don't look at the whole organization for capacity planning. Instead, look at the individual work teams, work groups, figure out which applications they're using, and their planned growth in personnel, and that will tell you what you need, right? So you don't just look at the whole organization and say, oh, it's going 50%. We're gonna, you know, put in a higher grade of cable, a higher grade of other hardware all throughout our system. No, instead you say, this part of the system needs to be upgraded. Maybe these other parts we can leave as is. So the goal, you get the capacity increases you need where you need them and avoid spending money to add capacity where it's not needed. Okay, so again, if you have time, I know it's finals week, but this is kind of an interesting old-timey look back into things, but some of the issues are still pretty relevant. Some of them aren't. Okay. So yeah, this stuff, one of the big things in that, first of all, identifying trends in major traffic sources. So look at the different applications, look at the expectations for that. How fast is the need for capacity growing among video streaming applications, right? As the quality of video goes up, you're sending more data. How many people are using which versions of it, that sort of thing. And the overall idea, categorizing traffic, right? So business traffic, of course, is important. You can have priority levels within that. Recreational traffic is not really important. You can allow that, like people going to Facebook or eBay, you can allow that if the network isn't too busy. And of course, malicious traffic, you try to identify that and block it all together. Okay, so again, the solutions, part of that was learning what's going on. So again, installing tools to measure traffic in detail on key links. So are you getting the quality of service for your critical applications that you hope to get? And in order to learn that, you have to install measurement equipment at various points in the network. and then expanding it capacity incrementally where it's needed. So you don't just throughout the whole network upgrade everything. You just figure out the points where you're going to need it most urgently and apply it there. And many points of the organization, you'll find, we don't really need to upgrade anything this year. Okay. Now, there's a couple different mechanisms for measuring. One is passive measurement. So passive measurement tracks the real activity that's actually going on the network. So it looks at things like data sources, what devices the traffic is coming from, what applications it is, what operating systems it comes from, and it's designed to detect malicious activity. So anything that's actually in the network, if it can be identified as malicious, of course you want to track that in order to block it. And it allows you to learn how particular applications are doing, how particular subnetworks, parts of the network are doing in terms of meeting their quality of service goals. So, for example, if you have voice over internet, you track how fast the packets are moving throughout the network, how many packets you can get from point A to point B in a given amount of time, and you assess quality of service that way. There is sometimes a problem that creates additional traffic through data collection. So if you want to grab a lot of data and at pretty short intervals, that can eventually end up being kind of a significant drag on the system. I mean, it's a few percent probably, but still it can be significant if your network is already pretty busy, or at times where it's pretty busy. One simple case of that is something called an SNMP trap. So SNMP, Simple Network Management Protocol, basically a protocol for reading what's going on in the network. And a trap is like an exception report. So if something unexpected and bad happens in the network, one of your devices that's tracking the system will send out a message to some sort of governing process that says, hey, here's something you should be aware of. You know, this particular application is not currently getting the quality of service it expects, and I'm letting you know that so you guys can do something about it. Active measurement, on the other hand, active measurement injects traffic into the system to learn network flow patterns. So think of this as essentially a simulation tool. So the network is running, it's doing its normal stuff. With active measurement, you can simulate the activity from a particular application and thus track its performance under a wide variety of conditions. So again, you're going to look at things like latency, packet loss rates, other variations in quality of service over time. Now, active measurement does inherently add network traffic, but typically it's pretty small. You might throw in like a few hundred packets or several hundred, and total volume, you know, about a meg of data is pretty negligible on a big enterprise grade network. But if you want to look at how things are on a particular link, right, every now and then you can run a controlled experiment and send in a batch of data and inject it. Now, active measurement, unlike passive measurement, you just check what's actually there. That's what you have to go with. But active measurement, you can do apples to apples comparisons, right? You can say, I am going to send in this same fixed stream of data at different times and under different conditions and see what happens. So if you want to do some kind of simulation testing, active measurement is good. If you want to see what's actually going on your network with the applications as they're typically being used, passive measurement is good. So in practice, most organizations use some variation of both. Other thing, flow and packet analysis. So flow analysis is looking at the entire stream of packets, looking at a flow of packets. And just like the simple network management protocol, you have the same sort of structure where there are exporters that capture the data, so they track what's going on in the system, and then they send it to collectors who pool it up and eventually transfer it somewhere for analytics. So flow is defined as a set of packets with some user-defined matching set of attributes, right? So it could be all the traffic from a particular source, or all the traffic to a particular destination, all the traffic using some sort of routing protocol, some sort of application, whatever. Flow is some sort of user-defined set of packets. And if you want to track how that particular subset of traffic is traveling through your network, well, use flow analysis for that. Packet analysis, on the other hand, is looking at individual packets, right? So looking at the individual things in the system. A big thing for this is detecting malware to the extent that you can. Now, it's very difficult to detect malware when the packet's data is encrypted, although it's not impossible. Cisco has claims to be pretty good at it. I'm agnostic on that myself. But anyway, when packet analysis, you're looking at individual packets. You can look inside the data to do what's called deep packet inspection, or you can look at just the headers to see, here's a set of packets from the, again, from the same source, from the same destination. All that information that's in the header, you can look at that. Packet analysis allows you to do things that aren't strictly flow related. So you can monitor individual machines, individual channels, individual switches. So flow analysis is a particular set of related packets, but packet analysis allows you, a more fine-grained analysis. Flow you do to get a batch of data and say, how is this flow going? Are we meeting quality of service targets? Packet analysis allows you to look at individual packets and consider things like, are packets arriving out of sequence? Or how many of them are getting dropped individually? Things like that. Okay. Last topic, we have a few slides here on prioritizing traffic. So, and this is important. Oh, we've had more time than I thought. Okay. So, key thing, routers are smarter than switches. Routers generally have capabilities that switches do not. And the key thing of that is routers can prioritize traffic better. They can say, have a list of rules that says, this set of applications, I'm going to transfer before I send data from this other set of applications. So routers, fundamentally, their big thing is they can prioritize data. Switches, not so much. Switches generally just repeat traffic forward. Something goes into the switch sends it onward. So it's basically just a connector between machines. Now, the way prioritizing traffic works, there's 3 core components. Number 1, you try to build your ideal traffic profile. So the network designers, administrators, whoever, they think, how should our system look? So that's going to include things like which applications get how much bandwidth and under what conditions. Typically, this is implemented as a set of rules so it can be done automatically. So you might have your high priority applications like A. It says here, application A gets whatever bandwidth it asks for. If that is a critical high priority application, yeah, give that whatever it needs. And typically those are more real-time urgent things. So again, voice over internet or transaction processing that you want to have happen basically instantly. Secondary applications might get some fixed or capped rate, right? As long as if there is capacity in the network remaining after application A has done whatever it's done, then B can get some share of that, whatever's left. And that might be capped at some level. And then application C, in this case, a low priority application, if A and B aren't using all the capacity in the network, then C can have some capacity to use. But anyway, this is what the system designers use. They categorize applications into how critical they are, and based on that, that's going to determine how much data, how much capacity in the network they get. The second part, traffic classification. So you have to have a mechanism in place for assessing what traffic you actually have on your network. So you make sure that all of the different categories you have, they're all assigned to one of these rules so that they can be appropriately handled. And then last, traffic shaping, applying those rules across your network and applications. So basically making the traffic flows conform to these ideal traffic profiles as best as you can. All right, traffic classification. So typically that's done to you do it in sort of grouping related applications together. So you don't necessarily want to come up with a custom scheme for every single application because a lot of that's going to be redundant. As far as you can, you generally want to group them into categories. It makes it simpler to understand and manage. So different traffic streams could be prioritized, right? If they're a critical time-sensitive one, could be throttled if they're not terribly critical, if slow is okay in some cases, or blocked altogether. Again, if you can identify malicious traffic or just not permitted recreational traffic, you could block that. And typical categorization methods, number 1, sources or destinations. So looking at the particular devices, that would be one thing. So you might have some part of your system that's very critical that operates, for example, communications between data centers. You might give that the highest priority, or depending on what you're doing with those data centers, you might give it a pretty low priority. If it's, for example, checking that the databases are properly synchronized, maybe that's something you push off and just do in the background as network traffic permits. Of course, specific applications or application ports. So, you know, if email is a low priority application, voice over internet or real-time video, probably something you want to have happen with minimum latency. The different packet characteristics, you could look at that. For example, looking at part of this information you're just going to get from the header. Other things you might look at is payload size, and some of that you could again associate with different applications. Legitimacy, so business traffic generally has highest priority, recreational, typically throttled, malicious, typically blocked if you can identify it. And last, you might even use some things like goals. So if any application that's involved in a transaction, well, transactions you typically want to happen pretty fast. File sharing, on the other hand, yeah, files can be pretty big. They're going to take a while under the best of circumstances. That's typically something you're going to push more to the back of the queue. And it doesn't really matter which application is doing it, right? This is, the point is, for example, if you're using an internet browser, of course, that's going to be a single application. So the single application is not going to be enough for traffic classification. You'll have to actually, in some cases, look at what that application is doing. If you're using a browser to do a transaction, yeah, that's going to have to happen pretty quick. If you're using a browser to do file sharing, that can happen pretty slow. Okay. And then traffic shaping. So traffic shaping is, again, how you apply these rules to control how traffic is routed. The big picture goal is you want to make your overall traffic conform to your performance targets as well as you can. I mean, there's always going to be a point where your network just gets too busy, but under normal circumstances, you should be able to have your traffic flows correspond fairly well to your ideal traffic profiles. If not, then it's time to redesign or upgrade the system. So you could do it in a couple of different ways. Number one, you could do simple prioritization rules. So categorize things by applications or sources or destinations and say, these are the important applications, give these priority, other things give them less priority. That's one way to do it. But of course, you can also have more complex rules that explicitly consider quality of service. So in a sense, they're going to be adaptive. So if it's a key application, you can make sure, you know, give this whatever bandwidth it needs to meet whatever quality of service target you have for it. So not specifically saying, this one goes faster, or this one goes second, or this one goes third, but just saying you need so much data, so much capacity right now to meet your quality of service targets. We're going to give you that much data. And a key thing, if you think you can have multiple high priority applications, right? This gives you a way to, again, do a more fine-grained allocation of resources there. So you could say, you know, I have this one application, even though it says it gets whatever data it wants, maybe it doesn't actually need all that much under the current circumstances. And so I'm not going to give it, like, max out the data it can use. I'm going to give it enough data to meet its quality of service targets and let the other critical applications have enough data to meet theirs as well. So yeah, you never want to give one single application an unlimited amount of data. It's better to say, here's your quality of service target. I will give you whatever data, whatever capacity you need to meet those quality of service targets. And again, if you look at the way resource sharing happens, if you have a bunch of users with one high priority application at the same time, you might have to pare down everybody's usage. Still, the application as a whole, it's going to crowd out other activity on the network, but to allow a large number of connections, you might have to dial down things like the video frame rate or the video quality to let everybody use the application simultaneously. Anyway, so yeah, more complex rules are possible. This simple prioritization scheme, it gives you an understanding of what's going on. But of course, if you have multiple applications that are at the same level of priority, you often need to have them share resources as well. Okay, so that's it. I could take a few minutes, I could talk about other stuff, but I'm not gonna. But I will ask if anybody has any questions they want me to address right now. Happy to do that. But the big thing for those of you who wandered in late, the big thing is the final exam. Let's upload let's use Paint. Big things. Number one, the list of presentations is available on Blackboard. So that's good if you want to check out what your other people are doing. you know, see how the other teams do theirs. Go check that out. Number 2, the final will be on Wednesday of finals week at 10:30 a.m. Okay. Again, administered through Blackboard. Number 3, FAQ and topics of interest will be posted later today. And number 4, Wednesday will be a review session. Okay, so Q&A, bring your Q's. That's it. That's what I got. All right, last call for questions. Anything on any of this stuff? All right. Well, it's been a